Let's continue with our ADA converter. So last time we said we have a digital analog signal A to D converter. Every process, we say it's if it's a digital, it's a discrete point along x-axis and y-axis at every grid line. So this point, this point, this point, this point, this point. So at every sampling time delta t, the process is done once. So normally we will have the clock to check the circuit. So we'll get to this point, discrete point and discrete amplitude in the y directions. Okay. Also, let's talk about the error to the AD converter. Well, first of all, we said it. We will have these so-called the saturations. So saturation errors. So due to these the voltage response of the AD converter, just like the up end, you have saturation errors. So AD converter. So how do we take care of this? For example, if the voltage can only as the converters or the signal can only accept certain voltage, or if you are too big, that's saturate above certain numbers. So when we say this range, we said we probably have a so-called full scale. I think we referred that last time too. Like unipolar, 0 to 10 volt, 0 to 5 volt, or bipolar, minus. If the response only accepts this certain range, what if your signal is too big or bigger than this range? So how can we deal with this? Or how do we correct? For example, if the converters have certain voltage, 15 volt, obviously cannot, you will saturate or above this range. Yes. Or you might, some situation you might have is just like you have AC along with BC signals. So you're at 10, but it's something superimposed with the DC voltage. Maybe it's but this one, the amplitude is small. However, this DC voltage turn is big, or maybe 15 volt or something. But the amplitude itself probably 0.1 volt. So how do we take care of this? Well, this one, if you DC, well, typically you can um, do this avoid by we said signal conditioning. Do something with this signal. Well, the easiest one, well, just make it smaller. So you can either do these, if it's too big, make it smaller. So we can attenuate the signal. Attenuators. Well, easy way to do is you make a typical op-amp circuit. If you remember, V in, V out, V in, V out, the transfer function will be R2 over R1 minus. So if it's too big, just make this is a ratio, R2 over R1, a ratio. So you can, this one we call attenuator, but if you make R2 greater than R1, we call it an amplifier, but it just depends on the value of R2, R1 to give you that. How about this one? We want to get the amplitude terms with like a ripples or sinusoidal signal superimposed by a constant voltage 15 volt. So the easiest way you can use offset we call DC offset removal. In other words, still keep the oscillation part, but get rid of this constant part. And you can minus 515, or sometimes you can use these what we call differentiators. You can get differentiated and then get this constant turned out because you have A plus B sine omega t. When you can take derivative, you get rid of this term. Yes, you might have the frequency, but if you know the frequency, you can get that back. But you can definitely take this constant out. Or you can just offset it, have another 15 volt. So you can only get the dynamics part and remove the constant part, constant voltage. So when we talk about conversion, AD conversion, the other kind of errors is what we refer to resolutions, quantization errors. The quantizations, typically we go from analog to binary, digital numbers. So what's resolution? Resolution, that's in terms of the y-axis, that's voltage. So that's amplitude. So again, same definitions, the smallest increment of voltage change. That can be resolved by an AD converter. So same as we have before. So if I have an n bit converter, n bit, so resolutions, the resolutions of this converter would be n bit. You will have how many number we can represent you with n bit converters, 2 raised to n power. So depends your voltage range, 4 scale. So depends on its unipolar or bipolar, but 4 scaled. In other words, if it's from 0 to 10, we divide this by divided by these numbers. Okay, or if you have then minus 10 to 10 resolutions. That's a voltage resolution per bit. So we know the resolutions. And then what is the uncertainty? What is the uncertainty? My computer froze. So what's uncertainty? Plus minus should be half of resolutions. So typical questions, how can you have a even finer or increase the accuracy? Of course, the more bits, the smaller uncertainty, smaller finer resolution you will have. So the uncertainty or the error can be reduced by adding more bits. More bits. Okay. So last time we already have this, but same thing if we just look at the same 3-bit conversions. So 3-bit. So if I have the reference or the 4 scaled, so 3-bit, 2 raised to the 3rd power should be 8. So 1/8, 2/8, that's 1/4, 3/8, 1/2, 5/8, 3/4, 7/8, and V are analog. So from the binary part, you will have 0, 1, 2, 0, 1, 2, 3, 3, 0 to 7 through. If you put numbers 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, the next one, 0, 1, 0 0 1 1 1 0 0 0 1 1 1 0 1 1 1. So for the analog voltage, it should be a continuous. Should be continuous. However, for the digitals, ideals, the digitals, you only have these. Each one part, you only have this. In other words, every voltage between 0 and 1/8 is zeros. And then between 1/8 to 1/4, you have this. And up to 7/8, even it's bigger, still it will stop, saturate. That's for conversions, AD converters. So you saturations. And what's resolutions? Resolutions is the one right here. It's between these resolutions. So the other type of error, the conversion error due conversion. Nonlinearity, zero offset, or maybe hysteresis. Repeatability, so on, so forth. So, but these are all provided by the manufacturer. So if we want to characterize overall conversion errors, overall, so again, rule sum square holds. So the uncertainty overall should be rule sum square. Still using rule sum squared uncertainty or errors. Okay, let's look at some examples. Let's start with the easiest one. It's the AD converter spec. The temperature change or variations is plus minus 10 degrees C. And these converters have voltage full scale that's from 0 to 10 volt and 12-bit. In terms of linearity errors, it's plus minus 3 bits. In terms of temperature drift error, that's 1 bit per 5 degrees C. So this is it. So we need to find overall errors or uncertainty, overall uncertainty in this conversion, AD conversions. These AD conversions. First of all, what's the resolutions? We can find the resolutions. That's full scale, V full scale over 2 raised to m. So that's 10 minus 0. And we have 12-bit, so to the 12. So that's 2.4 millivolt approximate. Now, meaning the resolution you have 2.4, and in terms of bit per bit. So first of all, error due to resolutions. Error due to resolutions. That should be half of resolution, 2.4. That's 1.2 millivolt. Again, uncertainty, a range of values to enclose the truth. So it's positive, negative, plus, minus. So these numbers. Now, linearity errors. Linearity should be plus minus 3 bit. Now we have 2.4 resolution per bit. So you have 3 bit. So 3 plus minus 3 bit times 2.4 resolution per bit. So you have plus minus 7.2 millivolt. Now, for temperature drift, that's plus, temperature is plus 10 degrees C. So plus minus in this variation here. Now that's 1 bit per 5 degrees C. So 1 bit per 5 degrees C. So give you totally plus minus 2 bit. What's the resolution? 2.4 millivolt per bit. So times 2.4 millivolt resolution per bit. 2.4 millivolt per bit. So we get 4.8. So in this conversion, we have three types of error. The from manufacturer itself, you have the linearity error, you have the drift, temperature thermal drift error, and from the conversion itself, we have the bit, so you will have the resolution error. So total, again, rule sum square, so plus minus 2 square plus 4.8 square, rule sum square one more time. 8.7 millivolt. Of course, when we have rule sum square, meaning when we estimate the uncertainty, it's all with confidence level of 95%. So overall error 8.7 millivolt.